Hi everyone, welcome to E635 Applied Linear Algebra. My name is Debisattam and you're watching the ninth lecture of E635, and this happens to be the first module. We have had a very long break. I hope you guys did well in your mid-semester exams. Uh, so today's lecture, we are going to look at a very particular structure that can be given to vector spaces, which allows us to talk about lengths of vectors and angles between vectors, and therefore we can talk about orthogonality, concepts like orthogonality and so on, right? However, we have to remember that the vector space for which this can be done must be defined over only real numbers or complex numbers, not other fields. Okay. Now, having said this, we have to remember that so far we have looked at only vector spaces and not any particular structure. We once defined what a vector space was, and then from there onwards, from those definitions of a vector space, from those uh, 10 axioms of a vector space, we derived all the machinery that we have done so far based only on those axioms, which means we did not pose any more or extra structure on the vector space, right? Here, however, we're going to put this extra nice structure, which allows us to talk about lengths and angles, lengths of vectors and angles between vectors for vector spaces defined over R or C. This structure is imposed via a function that takes pairs of vectors and maps it to the scalar, right? Either real numbers or complex numbers. Okay, this particular function is called the inner product defined on the vector space. Okay, so now in order to understand this idea of inner product and its usage more, we need to write some stuff. So I have to share my screen. Hang on. Okay, so it should be yes. Okay, so the idea comes from looking at R2 and R3, where we have this physical meaning attached to this, the so-called dot product. Okay, so think of R2, or let's say R3. Let us talk about R3. Let us concentrate only on R3. So in R3, suppose I have two vectors x1, x2, x3. This is three tuple, which is in R3. Suppose I have one more vector, one y1, y2, y3, another three tuple. This I'm calling capital X, and this I'm calling capital Y, right? Then X transpose Y is defined as is turns out to be x1 y1 plus x2 y2 plus x3 y3. Yeah, and in this situation, we can also talk about X transpose X, which happens to be X1 squared plus X2 squared plus X3 squared, and Y transpose Y happens to be Y1 squared plus Y2 squared plus Y3 squared. What we know from our experience is that this is nothing but the length of the vector x squared. This happens to be the length of the vector y squared. And in that case, it turns out that x transpose y is nothing but length of x, length of y into cosine of the angle theta between the two vectors. So if you like, this is my three axis. Here, I can think of one vector, this is x, and another vector, this is y, and suppose the angle between the two vectors is theta. In that scenario, this is what we have for this x transpose y. Okay. Over complex numbers, however, we have to be a little more careful. We have to do something like, so instead, if I'm on R3, if we have, instead of R3, if we have C3, then that's a situation. We have to define something like X transpose Y bar, the complex conjugate, which is X1 Y1 complex conjugate, X2 Y2 complex conjugate, plus X3 Y3 complex conjugate. Yeah, and why is this necessary? Because I want this I want this X transpose X to be the length, right? So this has to be, this must be the length square, which means it has to be greater than or equal to 0 for all X. Yeah, in C3, and in fact this has to be greater than 0 for all X not equal to 0. So it's 0 only for the 0 vector. If I want that, then you see, uh, if I indeed have uh, so this, for complex numbers I need to put this, because then only then I have, X transpose X bar comes out to be X1 bar plus what, sorry, plus X2 bar plus X3 bar, which is actually X1 squared mod squared, X2 mod squared plus X3 mod squared, which is indeed greater than or equal to 0. Yeah, if instead I had only X transpose X without the complex conjugate, then what would happen is, suppose X is some real number, real vector. Suppose, let X be a real vector, and I just do this. Then over complex numbers, I can consider this as well. And this would give me -1 into X transpose X. X transpose X being greater than 0, this has to be less than 0. But that's a problem over complex numbers, because over complex numbers, this is a legitimate complex vector. This is also a legitimate complex vector. And if I define the dot product without taking the bar, then I get that length is negative, which is absurd. Length comes out negative, which is absurd. And therefore, over complex numbers, we define the dot product with the complex conjugate. Yeah, this dot product, so you see, this can naturally be extended to Rn and Cn. Yeah, so we can define, so naturally we define for Rn and Cn, we introduce this symbol that this is the symbol of the map. So this is for Rn. This symbol here means the so-called Cartesian product. What it means is that I'm looking at a vector here and a vector here. I'm looking at the pair. So see, that is how the inner product works, right? It takes one vector, it takes another vector, and combines them somehow to give me a scalar. So that's why it's a function of two variables, two n tuples. That's why I have this Cartesian product to R. Yeah, so that is how this map is going to work. And how does this map work? Over Rn, it takes a vector X and a vector Y, and it maps it to X transpose Y. That is the inner product. Similarly, for complex numbers, these dots I'm using because these are the arguments which are empty now. We have to plug X and Y there. Okay. So that, by that I mean that this is nothing but X, Y by definition. Okay. Similarly, for complex numbers, yeah, for complex numbers, we have X, Y maps to X, Y, which is by definition X transpose Y bar. Yeah, is that all right? So that is how we define inner product in Cn and Rn. And there it has this natural meaning by extension from the natural meaning of these functions in R3 and C3, right? So this inner product is indeed uh, the two length multiplied the cosine of the angle between the two vectors. And of course, associated to this, we have the meaning of the length of the vector by taking. So we have this idea of norm, which is x is defined as the positive square root of x. And this definition works for both Rn and C, right? So far, so good. But remember, I mean, recall that in this course, we're not just interested in this Rn and Cn, but we have been looking at all sorts of vector spaces, which may not be just, tuples of n tuples of numbers. Yeah, they could be abstract vector spaces. Although we have seen that those abstract vector spaces can actually be identified with Rn or Cn by this the coordinate, by the idea of coordinate. But before that identification, one may also have such abstract vector spaces. And for those abstract vector spaces, the question is, how do we extend this idea of inner products to abstract vector spaces which are not necessarily n tuples of numbers? Okay, and that we will do just like we've done for vector spaces. We had put in these axioms to define the idea of a vector space. Similarly, we're going to put these axioms for the idea of an inner product, an axiom which will take out the essential ingredients of this X transpose Y or X transpose Y bar, and will sort of abstractify the idea. And with those with those points that we have abstracted, those essential points that we would have extracted from the idea of X transpose Y or X transpose Y bar, and we'll use them to define this abstract idea of an inner product. Yeah, I hope I made sense. Let us proceed with the definition, and then things will become clearer. So we are going to define, so the question is, how to define inner product on an abstract vector space V, which is defined over F, where F is either the field of real numbers or the field of complex numbers. This is the question. And the answer comes via this abstract definition. The definition of an inner product. Okay. So a function let me write it in the new line. It will look better. A function which takes pairs of vectors from the vector space V and maps it to the field F, which is either R or C, is called an inner product if it satisfies the following. What are these? Number one, it says that if I have two vectors, V and W, and suppose it, okay, let me do it this way. Let me do vector addition first. So suppose I have V1 plus V2 and V3. This must be equal to V1, V3 plus V2, V3, which means it respects scalar addition in the first variable. Number two, if I have scalar multiplication like this, then this must be equal to alpha V1, V2. So point number one and point number two together would be mentioned, would be stated in words in the following manner, that this is linear in the first variable. Yeah, remember that this function is such that there are two arguments for this function. It needs a v, it needs a w, both from the vector space v. So we call that, so when we're looking at the inner product vw, then v is the first variable, w is the second variable. And property one and property two together says that the function is linear in the first variable. Okay, now number three, if I have v and w, and I have w and v, I change the order, make the first variable the first. Sorry, let me use v1 v2 again, because I've been using v1 and v2. So v1 v2 and v2 v1. So suppose I have two. I've just interchanged the order of the two variables. I have made the first variable the second variable the first. Then how are they related? They are related through this complex conjugation. Right? So it's not exactly symmetric, but it's conjugate symmetric over complex numbers. Notice that over real numbers, this translates to, so this is equivalent in real numbers. Yeah, over real numbers, this turns out to be V1, V2 is equal to V2, V1, which means it indeed is symmetric. And number four, importantly, that V1 with V1, if I take, then this is always greater than 0 for all V1 not equal to 0. Yeah, and of course, if it is 0, then it has to be 0. Yeah, is it all right? So we can check that our idea of the standard inner product. Oh, by the way, before we move on, we have to notice this very interesting thing that, okay, the first two properties, so notice that 1 and 2, as I have been saying, 1, 2 together implies that if I have this inner product, alpha v1 plus v2, v3, this must be equal to alpha v1, v3 plus v2, v3. So that means it's linear in the first variable. However, 1, 2, and 3, these three together would imply the following, that if instead I have v1 and alpha v2 plus v3 like this, yeah, I thought this would be clear, but if not, then let me just mention that v1, v2, v3 are arbitrary vectors in V, and alpha is an arbitrary vector from arbitrary scalar from the field. Yeah. Now this, what would happen to this guy? You see, this would be equal to alpha v2 plus v3 v1 complex conjugate, which would by 1 and 2 imply that this is alpha v2 v1 plus V3 V1 complex conjugate, which is the same as alpha conjugate V1 V2 plus V1 V3, right? So ultimately what we are getting V1 alpha V2 plus V3 is equal to alpha conjugate V1 V2 plus V1 V3, which is almost linear, but except for the fact that there is a complex conjugation of the scalar that is being pulled out. Yeah, such a property is called sesquilinear. So it's not, so it's linear over the first variable, I mean linear in the first variable, but conjugate linear in the second variable. So that's why it's not bilinear, but sesquilinear. Sesqui means one half, right? Over real numbers, however, see, this complex conjugation will not appear, and it will turn out that it's linear in the first variable as well as linear in the second variable. So then it will be bilinear. So it's worth mentioning this point, that the way the axioms of an inner product is defined, this is bilinear, that is linear in both the variables in R, but is the so-called sesquilinear over complex numbers. So if the vector space is defined over real numbers, the inner product by definition is bilinear. Yeah, whereas if it is defined over complex numbers, then by definition inner product is sesquilinear. All right. Now, examples. Okay. Very simple examples, very easy to check. You will verify that all these properties are satisfied by the standard inner product defined on Rn and Cn. That is this. Let me do it over C directly. Cn to Cn. It sends, sorry, Cn, Cn to C. It sends XY pair to XY, which is by definition X transpose Y bar. And from Rn to Rn, it sends XY to XY, which is X transpose Y. You can check that all the properties are satisfied. I'll do it for the real numbers. X transpose Y, does it satisfy 1? Is it linear? So this means this would be x1 plus x2 transpose y, and that is indeed x1 transpose y plus x2 transpose y. Scalar multiplication, that does it come out? Yes, it does. Symmetry, yes. Greater than 0, yes. So let us check that. So let's do it for this itself. So number 1, x1 transpose, so okay, x1 plus x2 y is equal to x1 plus x2 transpose y bar. By definition, this is x1 transpose y bar plus x2 transpose y bar, which is indeed x1y plus x2y. So property number 1, check. Property number 2, alpha x y, by definition is going to be alpha x transpose y bar, which is indeed alpha x y. Property number 2 checked. Property number 3, property number 3 is x y is equal to x transpose y bar, which is equal to y bar transpose x, which is equal to y transpose x bar whole bar, which is the same as y x whole bar. Yeah, is that all right? So property number 3 is also checked. Property number 4, x is equal to x transpose x bar, which is the same as x uh, squared. This is greater than or equal to 0, and it's greater than 0 for all x non-zero, right? Okay, so this is fine. You can also go ahead and check that once again in Rn and Cn, if we define xy to be, say, so let's do it for Rn. Huh? So suppose we define inner product as x transpose A transpose AY, where A in Rn cross n is non-singular. It's a non-singular, that is invertible matrix. Then this also is an inner product. This goes to you as a homework. Do this check. In fact, it is an immediate attention problem. Check that this is an inner product. Check that this is an inner product. Yeah, related to this is a homework to you, not an immediate attention problem, but a homework. It show that if I have, say I'm on R2 to R2, so I'm defining an inner product here. How am I doing this? So x1, x2 vector and y1, y2 vector. Suppose it gets mapped to alpha x1, y1 plus beta x1, y2 plus gamma x2, y1 plus delta x2, y2. So this is by definition. Huh? So this is the definition of this. Your job would be to find out the condition on these numbers alpha, beta, gamma, delta, such that this is an inner product. Okay. Now, so far we're dealing with only things like tuples of numbers, but that's not the only case. Our purpose of abstractifying this idea of inner product was to be able to define inner product for more exotic vector spaces, not just in tuples of numbers. What could be an example of that? Say matrices. Okay, so suppose I have suppose I define inner product on complex n by n matrices. True. And how am I defining it? Suppose I have a matrix A and a matrix B, and I'm taking this to trace of A, B star. B star is the complex, is the Hermitian conjugate, no, Hermitian transpose, sorry, Hermitian transpose of B. So B star is B bar transpose. Okay. Yeah, check that. This is, sorry, is an inner product on C in cross N. Yeah, that's not all. You can also think of, so consider, so let us do this check, huh? Because it's not very difficult to do. So let's just do this verification. So number one, I have a matrix A1, I have a matrix A2, and I have this. This by definition would come out to be A1 plus A2 multiplying B star, and I have to look at the trace of this matrix. But trace of this matrix will satisfy that this is nothing but trace of A1 B star plus A2 B star. This is the same as trace of A1 B star plus trace of A2 B star. Trace, I hope you understand the meaning of, of trace. Trace is the sum of the diagonal elements. And this of course is uh, A1B plus A2B. So the first property is satisfied. Yeah, this is happening essentially because trace is a linear operator. Yeah, trace of A plus B, of course, is trace of A plus trace of B because it's sum of the diagonals, no? Okay. So property number one is checked. Property number two is trace of alpha A time A and B. Yeah, so this is trace of alpha A B star. But trace is sum of the diagonals, and when alpha is a scalar multiplication, then it multiplies every entry of the matrix. So in particular, it multiplies the diagonals also. So it means I can just pull out this alpha and find out trace of A B star, which is the same as alpha A. So number two checked. Number three is if I have A B, then that's A B star, trace of that. If I look at, now this is the same as, you see, trace has the property that is the same as trace of B star A, which is the same as trace of A, trace of, sorry, B A star, then take the complex conjugate. Yeah, maybe you may feel that I have skipped one step. Let me do it more. Let me simplify this. This is the same as trace of um, B star A I have. So this I can write as B A star and then take the whole conjugate. And complex conjugation of this, of a number, yeah, I'm just writing it when you check. This is what it is, which is the same as complex conjugate of B A. Perhaps the most non-trivial step is this one. This one. You just go ahead and check. Verify yourself that trace satisfies this property. Similarly, number four, so number three is checked. Number four says that if I have A and A, what would this be? This is trace of A star. Notice that trace of A star essentially means that I look at A and that whole square matrix, I just pull it out, I unfurl it and write it as one huge row. Yeah, then A star would be the conjugate transpose of that. Okay, so let me just explain what I just said. Suppose A is A11, A12, A21, A22, like this. Okay, and A star in that case would be A11 bar, A21 bar, A12 bar, A22 bar. In that case, trace of A star, you'll notice, is nothing but A11, A12, A21, A22, this row vector, and A11 bar, uh, A12 bar, A21 bar, A22 bar. Yeah, yeah, is that all right? Which is nothing but, the length of this vector, right? So of course, this is greater than or equal to 0 for all A, and it's in fact greater than 0 for all A not equal to 0. For all non-zero matrices, this is actually greater than 0, which means number 4 property also is satisfied. Okay, so that's how this also becomes an inner product. And you see, this is not our standard inner product kind of thing. This is inner product defined on a more exotic vector space, namely the space of square complex matrices. Over non-square matrices also one can define inner product like this using the idea of a trace. So if you think of this trace, this is actually nothing. This is defining inner product on Cn cross n via this trace is nothing but uh, identifying matrices in Cn cross n as vectors in Cn squared, yeah, C to the n squared, and they're defining the standard inner product. Okay. Now, number 4 is perhaps a little more exotic. So consider L2 RR. What does this mean? This is the space of all square integrable functions. Yeah, functions for which the square integration makes sense. That is, if belongs to L2 RR means integration, integration minus infinity to infinity f square t dt is a finite number. Hmm? Right. So on this space, this is also an inner product space. This is a vector space. You can check that it satisfies all the properties of a vector space. This also has an inner product defined in it. How do you define? So I have, so for the sake of simplicity, I'm just writing L2 to R, two functions fg define inner product as, gets mapped to the inner product. How is it defined? It's defined as integration minus infinity to infinity ft gt dt. That's it. This goes to you as a homework. In fact, an immediate attention problem. Let's show that this is an inner product. Show that this is an inner product. Okay, so we see that there are so many examples of such inner products. Yeah. Now, once we feel comfortable with this idea of an inner product, what we will see is what we can do with this inner product. When there is a vector space where an inner product is defined, what we can do with that inner product. And it turns out that we can do a whole lot of things, and it will have some really deep consequences as far as engineering problems are concerned. which we'll see in the next lecture though. Yeah. So now as a first step towards exploiting this inner product structure of a vector space, yeah, um, we define what is known as an inner product space. So this definition is kind of obvious. So a vector space V together with an inner product defined on it, this pair is called an inner product space. As simple as that. You have to notice that the same vector space may have different inner products defined on it. So as inner product spaces, they will be different. But as vector spaces, they may be the same. Like for example, in Rn, I can define the standard inner product, yeah, like X transpose Y, or I can define it using X transpose A transpose AY that we did before. So this two as both are defined on Rn, but the two inner products are different. So the two inner product spaces would be different. Okay. The next is this very interesting theorem. The next step towards exploiting this inner product structure. So suppose V is an inner product space. Suppose V is an inner product space, which means it's a vector space over R or C, and there's an inner product defined in it. Okay, then this function defined as from V to R, in fact, how is it defined? It takes a vector V and maps it to this positive square root of V. Yeah, this is a so-called norm. This function satisfies the following. Number one, it's so-called homogeneous. That is alpha times V. So alpha is an arbitrary scalar and V is an arbitrary vector in the vector space. W is also an arbitrary vector in the vector space. Yeah, for that, we have alpha V must be equal to alpha magnitude V. This is called homogeneity. Then V is greater than or equal to 0 for all V in V. And this is equal to 0 if and only if V is equal to 0. Number 3 is if I look at the inner product of V and W and look at the magnitude of that, that is always upper bounded by the magnitude of V and magnitude of W. This is called Cauchy-Schwarz inequality, right? And number 4 is V plus W magnitude, the norm, must be less than or equal to V plus W. Right, W looks really pathetic. Let me correct it. W. Right, this is called the triangle inequality. And these 4 properties will be satisfied by the norm. The moment we have the inner product defined on a vector space, so for every inner product space, there is a corresponding idea of a norm defined like this, and that norm will satisfy these 4 properties. Okay, this requires a proof. We'll see the proof when we come back for the second module. Okay, so see you in the second module.